Okay, so for everybody's favorite car, the 1994 Honda Accords, the braking distances, um, like how long you step on the brakes, how long does it take for you to come to a complete stop? Well, the average is 142 feet with a variance of 43 feet squared. That's weird. Calculate the minimum braking distance for a 1994 Honda Accord so that 27% have a shorter braking distance. 27% have a shorter braking distance. Well, we have a situation where we're going to apply the normal model. We have a continuous random variable here too. Everything's really perfectly set up, normally distributed. Right, so let's just go ahead and get a nice drawing out of right through it. Um, Here's a normal model. We're going to have to transform to z-scores, but we could at least start with x world, which is feet. We know that half are going to take a distance, or they're going to step on the brake, and then half, about roughly, are going to have distances more than 142 feet, half less. And that's equivalent to a z-score of z. Z's. Z is no longer alive. That's from the movie Pulp Fiction. It's a movie reference for you. Um, to move around on the x-axis, or the standard normal, or anywhere, we need to convert variance to standard deviation. So let's do that. So we need to figure out what the square root of 43 is. So yeah, you got to figure that out. Apparently didn't use the right notation in square. Oh, that's right. 43, 36, 7 something. 6.557438, right? Let's round it. I'm going to round it to 7. 7. Just don't tell anybody. I'm going to round it to 7. All right, let's write down what we got in X world. Sample, so we use X bar. It's a statistic. Just a reminder that we don't really know what the true average braking distance is, so we'll sample some cars and find out. Maybe we're the collision experts. All right. Then we have a sample standard deviation of, again, I round it big time. Like, you get in trouble for that. Right? We shouldn't round this if we were actual working for, with the Honda, the good folks at Honda. They would require a lot more both accuracy and precision there. All right, but we can move around the x-axis as follows. This is sort of a recap of the empirical rule and the stuff from earlier, but I think it's very helpful to look at that as well as we're getting more sophisticated here with our tools. You move up one standard deviation, move up another, and then not always, but usually 95% of the time I'll stop at 2 standard deviations above and 2 standard deviations below. I just can't fit the numbers in there, so that's how it goes. And then let's plug in some z-scores. I know that's 1, that's 2. Over here we have -1. Over here we have -2. I have not yet even begun to answer the question. Well, I have actually, because I converted variance to standard deviation. All right, so now let's, but we're building the construct here of everything. I mean, really, this is, as we'll see down the road, we'll be down the road, like when we get to the central limit theorem, when we get to the more sophisticated tools in the class, it'll all come back to the normal distribution because of this thing called the central limit theorem. All right, so let's go ahead and see what we got. We got a standard deviation. We've got perfectly normal. And there's something else here that we have. We have this 27%. So we're going to have to figure out what z-score traps 27%. And then we're going to go move back to X world, which is why I wrote it. All right. So here's the thing we're going to have to use. I know what we have to use. Just trying to figure out a color. So just relax. Z, we don't know what that is, right? We even in some problems give it like a star or 0 or naught. X, do we know anything? Let me put a question mark here. Oh yeah, we got that. 142 over, all right, we got that too. We're missing two things, so we're going to get one. And which one is that going to be? There you go. We're going to figure out what that z-score is. So what z-score traps 27%? Now the question is, do you want to trap 27% on the left side or the right side? 20%, 27% shorter braking distance. Shorter, less than. Somewhere over here it looks like. Oh, think about the empirical rule. Right? Right? Think about it. Just by the empirical rule from way back in the day, 2 weeks ago, how much stuff's to the left here? That's right, 16%. So it's not going to be a z-score of -1. It's going to be a z-score of... Wait a second, we already did this, didn't we? We did. Remember before? You're going to go into the body of the table, your standard normal table, and you're going to look for the closest z-score to 0.27, and it should be around -0.61. Negative 0.61. You'd say that's 27.09%, Danny. That's not right. I say, you're right. It's just an approximation. And that would be the end of our conversation. Negative 0.61, that's your z-score. So we have a two-step equation here to solve. Dot. Okay. Negative 0.61 z-score equals x minus 142 divided by 7. And what we want to do is get back to z. We have z world for once. And we want to get to x world. Stopping. Got to get up here. What is that? Solve for x. 7 times negative 0.61. I'm on it. 7 times 0.61. And that's got to be negative. So we have negative 4.27. Then plus 142. And we get, as they used to say in that TV show, this is my final answer. 138 feet. I'm just rounding. My rounding is it's upsetting for a lot of people. So if you're upset, you're not alone. You're very normal. But these are all approximations, and I think the rounding just helps you remember that. But I could be wrong. But the answer is 138 feet, thereabout. 138 feet. Let's zoom out here. Just sort of put it all together. You just pause it too. It's probably even better. Try it on your own.